Hello and welcome. So you may recall at the beginning of this semester, I introduced calculus, suggesting that there are two main branches of calculus. There is differential calculus and there is integral calculus, each of which can be interpreted geometrically. The differential calculus, we use the interpretation of the slope of a tangent line, and we analyze functions using the slope of the tangent line as a geometric construct for the instantaneous rate of change. And in integral calculus, the geometric construct we use is the area under a curve, or a bounded area. Okay, so generalized two-dimensional regions, and we have interpretations for that to discuss as well. The section here, section 4.9, that we're taking a look at, marks the transition between the differential calculus to the integral calculus. And we're going to start by defining what these things are called antiderivatives, and here it is. An antiderivative is the reverse of the differentiation process. That is, if you already know what the derivative of a function is, then the original function would have been the antiderivative of the derivative. Take, for example, the function f of x equals x squared. We know the derivative of x squared is 2x. Therefore, an antiderivative of 2x would have been x squared. That is, when we're asked to find an antiderivative of a function, the question we are asking is, can we determine a function or a family of functions such that we are currently looking at its derivative? We certainly can interpret that geometrically. We had graphed the derivative function, given a function f, or in context perhaps a position function. We can use that graph in order to construct the function's derivative graph. Alright, so we can graph f prime using f, or we can graph the velocity function using the position function. Well, anti-differentiation would be kind of a reverse of that process. If we're already looking at a graph that is a derivative function, can we determine what might have been a function from which it was derived? So anti-differentiation, first of all, will require that we understand the process of differentiation, the rules of differentiation, very well, so that we have a catalog of the types of derivatives, for instance, for different families of functions, and that's a main part of this section here, is dealing with, do we recall how to take the derivatives of different families of functions, as we have been doing now for several weeks. If we know how to find the derivatives of a particular family, then we have the beginnings of how to find the antiderivatives for that family. And then in future sections, you'll be looking at how to reverse the other rules of differentiation. That is, how do we reverse the product rule? How do we reverse the chain rule? How would we reverse the quotient rule? And then, and most of that is going to take place in your next semester of calculus, your Calculus 2 course. Here we're going to start with the antiderivatives for different families of functions and some of the interpretations we have for it. And in a future section also, certainly, we're going to be looking at the geometric interpretation, going back to that idea of the area of a bounded region. It can be interpreted through the use of an antiderivative function, and that is the geometric construct of integral calculus. And there's some caveats to that. It is not always possible to find an antiderivative. For example, although we know that when the function is differentiable, we can find the derivative, it may be that a function has theoretically an antiderivative, but we may not even be able to actually calculate it. And in your future course, Calculus 2, you'll take a look at a point in the semester at how you can still determine geometrically areas of curves and interpret analytically those responses to questions for, well, what do you do if you can't find an antiderivative explicitly? Okay. So you have a lot of work ahead of you in integral calculus. Okay. A lot of it is based around doing anti-differentiation techniques. Okay, so we're going to start by finding the antiderivatives of different families of functions, such as reversing the general power rule, reversing the rule for trigonometric derivatives, exponentials, logarithms, hyperbolic functions, right? The inverse trigonometric functions, okay? Since we know how to differentiate, then we should be able to looking at the derivative, we should be able to know what was the function that it was derived from. And we'll also be putting together families of antiderivatives, so-called general antiderivatives, through the addition of a constant, and we'll generally be using C as that constant initially. We can also use D, E, F, or we can use with subscripts C1, C2, C3 if we end up with multiple constants of antidifferentiation. Oh, and the reason for that is, if you consider that an antiderivative is a function whose derivative you're currently looking at, remember that the derivative of every constant is actually 0. Okay? We'll take a look at this in a moment. Then we'll also look at problems where we'll have to find particular functions when given information and given conditions. As a context, for instance, suppose that in an application problem, suppose that we're given a velocity function and we're told what the original position, the initial position of an object was. So if we're told the initial position of an object, let's say somebody throws a ball off of the top of a building. Okay, if we know the initial height of the building, that would be an initial position. And if we know the velocity at which they threw the ball, that would be an initial velocity as well. So if we're given, for instance, an f prime of x function, and if we're also given some point that was on the original curve y equals f of x, we would want to find the particular function, which would have that point and which would have that derivative. And we can extend this to higher derivatives as well. If we're given a second derivative function, f double prime of x, but if we're also given some point on the first derivative curve and a point on the original function, we should be able to, through antidifferentiation and the use of arbitrary constants like plus c, we should be able to reconstruct the original function f, for which we're looking at its second derivative along with a couple of initial conditions. So I've included for you at this section some typed notes. I strongly urge you to take a look at them. Okay, read through these notes I've designed for you. Okay, there's the definition of the antiderivative taken from your textbook. Okay, and the theorem which says that if f, this is uppercase F right now, can be often used as the notation then. Okay, that would be an antiderivative of an initial function with a lowercase f. Okay. Another type of notation could be, well, suppose that you're looking at a function y equals f prime of x. Then the antiderivative of f prime would be f of x, regular lowercase f of x. It's relative to each other, the symbol that we use. But if we wanted to find the antiderivative of lowercase f of x, we might call that antiderivative uppercase f of x. Okay. Okay, so we have built into here, since we've been studying derivatives for so long, we have built into here that we can always check to see if we have found an antiderivative. If we actually have found an antiderivative function, uppercase f, then it should be that the derivative of that function we found would give us back the original function we started with. And every time that we find an antiderivative, we actually need to express that we have found a family of antiderivatives through addition of an arbitrary constant. The reason why is, again, we check our answer. We check to see if our antiderivative is correct by checking that its derivative gives us back the original function. And recalling that the derivative of a constant is always equal to 0, then that means there's actually going to be infinitely many antiderivatives, but they will all be relatable to each other. They all belong to some family. Infinitely many antiderivatives for any given function f. For example, let's take the function lowercase f of x is equal to x squared. What is an antiderivative to that function? That is, can we find a function, call it uppercase f of x, such that the derivative of that big F of x would give us back an x squared? Well, one possibility is big F of x is x cubed over 3. How do we know? How can we check that this function right here, x cubed over 3, is an antiderivative to x squared? Well, if it really is an antiderivative, then we should take its derivative. The derivative of x cubed over 3, if it is an antiderivative, should give us x squared. And we know how to take the antiderivative of x cubed over 3 by the general power rule. We can factor out the constant 1/3, and then we would multiply by 3x squared by the general power rule. So the 3's would cancel each other out, and we're left with just x squared. The derivative of this big f of x function would be little f of x. But this is not the only function whose derivative is x squared. If we added any constant we want, okay, a positive number, a negative number, could be whole number, integer, fraction, decimal, any constant that we want. Notice that the derivative of each of these functions would also be x squared, because the derivative of a constant, such as 5, the derivative of 5 would just be 0. So for any function that we're given, the question of finding an antiderivative would actually yield a family of functions which are antiderivatives. In order to get a function whose derivative is x squared, we would want to reverse the general power rule, because we apply the general power rule in differentiating to get to x squared. And we always want to add an arbitrary constant as well. Okay, so the general antiderivative for f of x equals x squared. Okay, find the general antiderivative for f of x is equal to x squared. So how can we do that? We can reverse the general power rule. And so the general antiderivative, let's call it big F of x, is x cubed over 3 plus c, where c represents any constant. So this is a family of functions. Now in general, how do we reverse the general power rule? Let's take another look at it closely. The general power rule is defined for any function f of x equals x to the n can be any real number. Then the derivative of that is done by multiplying n times x to the n minus 1. In other words, these are the steps, right? The steps that we outlined for the process of the general power rule. We first multiply by the exponent. We move the exponent to the front, if you wish, multiply by the exponent. And then we subtract 1 from the exponent to get a new exponent, right? Those are the two steps in exactly that order. If we hope to reverse this process, we should read back these steps in the opposite order and do the opposite, right? And do the opposite operations. That is, the reverse of this process would be that we would add 1 to the exponent, right? That would be the opposite of subtracting 1 from the exponent, would be adding 1 to an exponent, and then dividing by the new exponent. That would be the opposite of multiplying. Right? So if you imagine, any invertible process, if you can outline that it is particular steps in a particular order, if you wanted to undo that process, you would reverse the order and have to reverse the steps themselves. So if we're given a function f of x is equal to x to the n, and if we wanted an antiderivative of that function, this process suggests that we should first add 1 to the exponent. That would give us x to the n plus 1. Then divide by the new exponent. So we get x to the n plus 1, and then divide by n plus 1. Now let's check to see if that really worked. If we're given f of x equals x squared, then the possible antiderivative, one possible antiderivative, would be add 1 to the exponent. That would give us the power 3, and then divide by that new exponent, x cubed over 3. And again, we can always check to see if our antiderivative is reasonable by differentiating it. That is, we are relying heavily on our ability to take derivatives very well at this stage in order to be able to determine how to find antiderivatives. And again, in the future course, you're going to run into functions whereby you may be able to take its derivative just fine, but finding an antiderivative can be really nasty. It may even not be possible to find an antiderivative for certain functions. Okay, so we reverse the general power rule. That is, we have as long as this thing actually exists. When would this not exist? This antiderivative would not exist if the denominator was equal to 0. And if this denominator is equal to 0, that would be when n is negative 1. In other words, if you were dealing with the particular function f of x equals x to the negative 1, right, this process of antidifferentiation is not going to work because it would force us to divide by 0. So let's take a closer look at that one particular function. What happens if n is negative 1? Well, that would be the function 1 over x. What is the antiderivative for 1 over x? That is, which function has as its derivative 1 over x? We previously saw that the derivative of natural log of x is 1 over x. Right, we found that through using invertibility, okay, and implicit differentiation. But not just natural log of x is 1 over x. Remember that there was an issue of domain when we compare the natural log of x to the 1 over x function. The natural log of x has a domain where x has to be greater than 0 specifically. But 1 over x allows for x to be either positive or negative. It's just that x can't be equal to 0. So in order to make this work, we actually need to define the natural log of the absolute value of x as the true antiderivative of 1 over x. And then to express the family of functions which are antiderivatives to 1 over x, we would have to add a plus c. Okay, so let's recall. I'll recall for you here from previous notes that the derivative of the natural log of x is equal to 1 over x. Demonstrate that that's true. If we let y equal the natural log of x, then we invert that. Okay, if we invert this relationship, we get e to the y is equal to x. And then if we apply implicit differentiation to this, that is, if we wanted to find y prime to prove that this is true, right? Implicit differentiation, we get e to the y times y prime is equal to 1. That's implicit differentiation applied to this derivative with respect to x. Solve for y prime. Then y prime is equal to 1 over e to the y. But what's e to the y? We said right here that e to the y is equal to x. So therefore we have y prime is equal to 1 over x. So we do in fact have that the derivative of the natural log of x is 1 over x. Or recall the issue of domain. The natural log of x, okay, has domain where x must be strictly greater than 0. But 1 over x has the domain where x is not equal to 0. That is, x could have been negative on the right-hand side of this equation, but x is not allowed to be negative on the left-hand side. This is important to consider then, right, if we are taking the antiderivative of 1 over x, okay, because that's what we would be given initially. Right, if we are asked to find the derivative of the natural log, we should consider what is the domain of the natural log, and therefore the result would have to share the same domain. If we're asked to find the antiderivative of 1 over x, we should consider what is the domain of 1 over x. All right? If we're asked to find the antiderivative of 1 over x, that is, we're given 1 over x, we should have the initial assumption that we are dealing on the domain of 1 over x. That is where x is not equal to 0. And when we answer the question, well, what is a function whose derivative is 1 over x? The answer can't be natural log of x, because natural log of x doesn't have this as its domain. So also we'll recall then the natural log of the absolute value of x has as its derivative 1 over x. And here the domain of both sides is that x is not equal to 0. Okay, the natural log of the absolute value of x, the domain is that x is not equal to 0. And the domain of 1 over x is also the domain of 1 over x is also that x is not equal to 0. How did we define this derivative? How did we find out that this was true? We defined the natural log of the absolute value of x piecewise. We said, well, that's equal to the natural log of x as long as x is greater than 0. But if x was less than 0, if we plugged a negative number in here, the absolute value is going to flip that over to make it the opposite sign. And then we take the natural log. Okay? And then we use the chain rule to deal with the derivative of the second part. So we have the derivative of the natural log of the absolute value of x then, okay, is equal to, on each of these pieces, we get the derivative of the natural log of x, which is 1 over x, as we already showed above. And the derivative of the natural log of negative x would be, by the chain rule, 1 over negative x times negative 1. That's the chain rule being applied there. Okay? And that's if x is less than 0. But 1 over negative x times negative 1, okay, is just 1 over x. Right? So therefore, the derivative of the natural log of the absolute value of x is 1 over x. And here we are, we are consistent on both sides of this equation that the domain will be that x is not equal to 0. Okay? So now, if we're asked to find the general antiderivative, of f of x equals 1 over x, the way this is stated, we are assuming that we're dealing with the domain where x is not equal to 0. That is, we are assuming that x is allowed to be negative, because this is what we're given. So the answer to this would be that we have a function big F of x, okay, would be the natural log of, it would have to have the same domain as what we were given, so the natural log of the absolute value of x. And then to make it the true general antiderivative, that is a family of functions, we add the arbitrary constant c. And again, to check our answer, we should take the derivative of the big F of x. Okay? If it is an antiderivative, then the derivative of big F of x would be little f of x. And we expect the answer then to give us back the original 1 over x, okay, over the entire domain. So the derivative of the natural log of the absolute value of x, as stated above, is 1 over x, and the derivative of the constant c would just be 0. So this verifies that it's true. So we found a general antiderivative to 1 over x. Now recall that 1 over x is a power function. It is x to the negative 1. Okay, so we have found the general antiderivative for x to the negative 1. And that completes our reverse of the general power rule. Okay, so that's stated and explained in the type notes, and again here. Right? Reverse the general power rule. If f of x equals x to the n, okay, then big F of x is equal to either x to the n plus 1 over n plus 1, and then plus c. That's if n is anything other than negative 1. Any real number other than negative 1, because then it would be undefined. Okay. But if n is specifically equal to negative 1, that is, we're dealing with the function 1 over x, its antiderivative would be the natural log of the absolute value of x plus c. Okay. That is the reverse of the general power rule. Okay, we should be reversing all the other rules of families that we've previously discussed in the course. And you'll see a lot of them here outlined in this table. Okay, there's the trigonometric functions. For instance, we have that the derivative of the sine function is cosine, right? We recall that derivative of sine is cosine. Well, therefore, it would be that the antiderivative of cosine would be sine. That is a particular antiderivative. What is the general antiderivative to the cosine function? It is the sine function plus the arbitrary constant c. Recall that the derivative of e to the x is e to the x. Therefore, the antiderivative of e to the x is e to the x. And the general antiderivative of e to the x would be e to the x plus c. A particular antiderivative is when a specific constant value c has been selected. In each of these particular antiderivatives, the constant that has been selected is equal to 0. Okay, it is one potential antiderivative. Okay. What else? We have other trigonometric functions. Recall that the derivative of tangent is secant squared. Therefore, the antiderivative of secant squared x would be tangent x. Right? Okay, find the general antiderivative for the function, how about f of x is equal to secant x tangent x. How do we find the antiderivative? By using the catalog of the derivative functions for the different families that we already know for this particular example. Because this combination, secant x tangent x, is the derivative of a function that we have studied before. That would be the secant function. So f of x equals, big F of x equals secant of x is a particular antiderivative to this, but the general antiderivative to this function is secant x plus c. How do we know that that's the answer? Check the answer. What is f prime of x? F prime of x is the derivative of secant x plus c, and the derivative of secant is secant x tangent x, and the derivative of a constant is 0. So the derivative of our result here is in fact equal to the original f of x, and we've created a family of such antiderivative functions. So there is not a rule here to apply in reversing this the derivative of a trigonometric function. It's not done by a rule algorithmically like the general power rule was done algorithmically. It's not like an add one and then divide by the result kind of a situation. It's not an algorithm. It's instead a memory of a catalog of derivatives that we have already studied in the past. What is also going to be key is that we are applying algebraic technique and perhaps trigonometric simplifications, things of that sort, in order to make the calculus easier when we have a chance. Right? If the derivative of secant is secant tangent, then the antiderivative of secant tangent would have been secant. That is a particular antiderivative. Okay, recall the 1 over 1 plus x squared function? That was the derivative of arctangent of x. We should know that so that we can say when we are looking at 1 over 1 plus x squared, we should know that its antiderivative would be the arctangent of x plus c if it was a general one. The hyperbolic functions, right? The derivative of sinh was cosh, the derivative of cosh was sinh. So the antiderivative of cosh is sinh. The antiderivative of sinh is cosh. Okay? There are certain functions that we have studied so far that we know how to take their derivative, but we have not yet discussed how to find their antiderivative, or even if that antiderivative exists. So one such function is the arctangent of x function. We know the derivative of arctangent is 1 over 1 plus x squared. Okay, that was shown by invertibility, the implicit differentiation, and the use of right triangular trigonometry or the Pythagorean identity. That's how we can show that the derivative of arctangent is 1 over 1 plus x squared. But to find the antiderivative of arctangent, you're going to have to go into a Calculus 2 course in order to study how to do that. We need more than what we have in this course in order to find an antiderivative to the arctangent function. Recall the exponential function. The derivative, okay, the derivative of b to the x. Let's take a look at that again. Recall that the derivative, let's say d over dx of b to the x is equal to b to the x times the natural log of b. Okay, where this is well defined, and so that's where b is greater than 0 and b is not equal to 1. This was a rule that we were able to establish by using, for instance, a change of base. We could change the base here from b into the base e, the natural constant e, okay, through the use of the natural log, right? We were able to write b to the x as e to the natural log of b to the x, which is equal to e to the x ln b, okay? And then we could take the derivative of this, right? So if we have y is equal to this, then y prime, by the chain rule then, is equal to e to the x ln b times the derivative of x ln b. The derivative of this x ln b would just be the natural log of b, because that's a constant. And then rewriting e to the x ln b back in the original form b to the x, we get b to the x times the natural log of b. Right? So we recall that. right? That we had already established that was true. Well, now what is going to be then the antiderivative of b to the x? We have that the derivative of b to the x is b to the x times a constant. Okay. Let's find the general antiderivative, okay, of the function f of x is equal to b to the x. Well, if the derivative of b to the x is done by taking b to the x itself times a constant, where that constant is natural log of b, then the antiderivative is going to be b to the x, where we divide by the constant natural log of b. Because dividing by a constant would be the opposite of multiplying by a constant. And then we would put a plus c, okay, an arbitrary constant c. We can check the answer. We're saying, well, what is f prime of x? Big F prime of x. Okay, so that is the derivative with respect to x of b to the x over the natural log of b plus c. All right, now because the natural log of b is a constant, we can factor that out of this first term. So 1 over the natural log of b times, now we have the derivative of b to the x, okay, and then plus, then we have the derivative with respect to x of the constant, right? So we have 1 over the natural log of b. Our derivative of b to the x, as we've already discussed, is b to the x times the natural log of b. And the derivative of our constant is 0. And now our constants will cancel each other out, so we are left just with b to the x, and that was our original function. So that verifies our result. Okay, so that would be true for any base b that is greater than 0 and not equal to 1, even for e to the x. Now, because for e to the x, the natural log of e is just equal to 1. So the derivative of e to the x is e to the x. E to the x times 1, right, which is e to the x. So the antiderivative of e to the x would be e to the x divided by 1, which is just e to the x. And then plus c to get the family. Okay, the general family of antiderivatives. Okay. All right, so what happens if we're given something like maybe a product? How do we find an antiderivative of a product at this stage? Well, we haven't discussed how to reverse a product, right, in differentiation. Okay, that is, we don't know the reverse of the product rule. Now, we just reversed a product where one of the factors of the product was a constant, right? This was a constant right here. Right? The reverse of multiplying by a constant is dividing by a constant. But that's not how, just as we know that the product rule is not just the product of the derivatives of two functions, okay? The reverse of the differentiation for a product is not just something like you find the antiderivative of each of the two functions and multiply those antiderivatives together. It requires a further analysis in actually reversing that product rule by a process called integration by parts. That is part of a Calculus 2 course. But in this course, what we can do when we're looking at a product is, well, we did a product of functions here. What was the antiderivative for secant x times tangent x? That was a known antiderivative. That was known to be secant x. And so we knew that because we had a catalog of derivative functions. But for this one, well, it looks like power rule stuff going on. What we should do is we should apply some algebraic technique in order to simplify this. If we distribute this root x in this example, we would get a string of power functions. We're going to get 2 power function terms here. And then we can do the antiderivative of each term. Fortunately, we have that, in doing an antiderivative, we can still factor out a constant, just like we did with derivatives. And we can distribute the anti-differentiation operator, distribute that through an addition and through a subtraction as well. Okay, so if we have 2 terms, here I have 2 terms separated by a minus sign, we can find the antiderivative term by term. That we can do. We cannot find the antiderivative of a product, not yet. Okay, unless it's a known, right? Unless it's a known antiderivative from our catalog of known functions. All right, so I've distributed the square root of x. I've rewritten the two terms as power functions, and then we have reversed the power rule. Right? Again, we have x to the n functions here, where n is not -1. So what do? Add 1 to the exponent, and then divide by the new exponent. In both of these terms is what we do. We add 1 to the exponent, and then divide by what is the new exponent. And the constant gets factored out to the front in each case. Right? The coefficient gets factored out to the front. And then we need to simplify this. And the last thing to do is to tag on the plus c. C can be any constant. Okay? We need to allow c to be flexible, to be any constant. We don't choose c to be a particular constant unless we are given some other condition that the function also would need to satisfy. And we'll take a look at examples like that. How do we check to see if our answer is correct after all that work with all those fractions inside of fractions? You check to see if your antiderivative is reasonable by taking its derivative. Just always remember to put that plus c in there. Okay? Because the derivative of a constant is always going to be 0. You're going to lose that bit. But take the derivative of your result by applying the general power rule and seeing that you get back, yes, the original result. Right here I factored out the square root of x in this last step to reverse the distribution. What about a quotient? How do we reverse a quotient? We don't have a reverse of the quotient rule in this course. In fact, in your Calculus 2 course, you won't need to reverse the quotient rule itself. Every quotient can be rewritten as a product, where you take the denominator and write it to the -1 power. So in fact, the reverse of the quotient rule can be done through a combination of reversing the product rule and the chain rule. All right? And we have not talked about either of those processes, the reverse of either of those processes yet in this course. So this is not, this is not the, a function that is a derivative of some other function that we already know. Okay, so what do? Let's apply some algebraic technique. Okay, and an algebraic technique that can work here is we can do long division. We can rewrite this rational function here as these two terms through use of a quotient and a remainder term over the original denominator. Now, how do we find the antiderivative of this? Term by term. What is the antiderivative of a constant? That is, what kind of a function would have a constant as its derivative? And the answer to that would be a linear function. Now, it is really the general power rule. Okay, find the general antiderivative of the function f of x is equal to c, where c is a constant. Well, consider that we can write any constant, okay, in a power function form by choosing the constant times x to the power of 0. So now it's rewritten as a power function. And we can then find the antiderivative of this, okay, through the reverse of the general power rule. So we get cx to the 0 plus 1 divided by 0 plus 1. And then we have to add an arbitrary constant. Oh, but we've already chosen c to start with, so we'll need a different constant. So I'll choose d. Okay, so our antiderivative to that given constant, let's simplify this. 0 plus 1, of course, is just 1, so we have cx plus d. So for example, if f of x is equal to 2, then big F of x, the antiderivative, would be 2x plus, well, I can call it d for this to keep it consistent with this example, but some arbitrary constant. Another choice we can make for when we have more than one constant is, again, to use subscripts. We can call this C1, we can call this C2. That way it allows for us to have an unlimited supply of constants if needed. Okay. Because otherwise we would run out of letters of the alphabet here. Right? And we could choose subscripts instead. Okay, so an antiderivative of the constant 2 is 2x. What about an antiderivative of 3 over x squared plus 1? Well, 3 over x squared plus 1 is the same as 3 times 1 over 1 plus x squared. All right, and I'll do another example like that. And the antiderivative of 1 over 1 plus x squared is the arctangent function. Okay, so find the antiderivative f of x, the general antiderivative this is asking for, if little f of x is equal to 3 over x squared plus 1. Well, f of x, the given function, can be rewritten as 3 times 1 over x squared plus 1, and I'm just going to write it as 1 over 1 plus x squared because that's just the way I'm used to seeing the formula written. We know the antiderivative for that. Okay, so then the antiderivative, big F of x, first off we can factor out the constant so we can leave the 3 in front, and then we have the antiderivative of 1 over 1 plus x squared, which we know as the arctangent of x. And then we create a family of functions by tagging on a plus c. So it's a combination of algebraic technique now and knowing the antiderivatives for some functions, such as the 1 over 1 plus x squared. The antiderivative of that is arctangent, such as secant x tangent x. The antiderivative of that would be secant x. Here's a secant theta tangent theta. Its antiderivative is secant theta because we know it. Okay, and we know the antiderivative of e to the theta is e to the theta. And for other terms, it might be that we have a rule, like the general power rule reversed, or x to the negative 1, where we need a natural log of the absolute value of x, or b to the x, where the antiderivative would be b to the x divided by the natural log of b. Some keys to antidifferentiation: know your derivatives really well. The basic rules of differentiation, know those well, and know the sort of the catalog of the derivatives of different functions as you're used to seeing, so that you can find the antiderivatives. And check your answer. Take the derivative of your answer to make sure you're getting back the original answer. And always remember to put the plus c for a general antiderivative as well. Brute force is not always the best. That is, just going straight for trying to do the calculus on what you're given is not always the best choice. If you just tried to take an antiderivative of this I'm saying brute force, I'm saying by ignoring all the algebra and just trying to go straight for the answer right away. If you tried to take an antiderivative of this by applying calculus directly to this expression, it's not going to work. There is no way to manipulate doing like an antiderivative of the top versus an antiderivative of the bottom and putting it in some kind of quotient rule format or anything like that. It really does require that you go with an algebraic approach here for this particular exercise. That is the way to do it. So you need to, instead of brute force, maybe finesse. Be able to apply algebra and trigonometry and techniques that you have otherwise learned outside of a calculus course, and use it in order to make the calculus easier to do. Even if the case is that there may be a technique in calculus that would have worked, in a lot of cases also, doing a little bit of algebra is going to make the calculus even easier. Just do lots of practice, okay? And in your Calculus 2 class, you'll be spending pretty much the whole semester dealing with antidifferentiation, its interpretations, and what happens when you can't find an antiderivative, for example. Okay, back to differential equations, which we were introduced to a couple times previously in this course. That's where you can relate a function to one or more of its derivatives. First, we're introduced to a second order ordinary differential equation in the hyperbolic section. We can say because the second derivative of a hyperbolic function is equal to itself, like the second derivative of the sinh function is the sinh function. And we saw the first order ordinary differential equations as well in the exponential modeling section for this course. So in general, again, when you can relate a function to one or more of its derivatives. Okay. Well, finding some solutions to some differential equations can come down to anti-differentiation techniques. This is only scratching the surface for differential equations. Here's an example of an equation. Can we find a function f such that we know what the second derivative of f is? Well, we can by doing anti-differentiation, right? So we can find f prime of x because it's the first antiderivative of f double prime of x. And in this case, that means we can go term by term and we can reverse the general power rule. So in the first term, which given x to the sixth, In the second derivative, well then in the first derivative we would get x to the 7th divided by 7. Add 1 to the exponent, divide by the result. The second term, we factor out the negative 4. We add 1 to the exponent, divide by the result. So we get x to the 5th over 5. Third term, add 1 to the exponent, divide by the result. Fourth term is a constant. And the antiderivative of a constant is going to be a linear function. So we get x, because the derivative of x would be 1. And then we remember to add the constant c. And now we have to go a step further, which is then to find the antiderivative of our antiderivative. That is, because we need the original function f. So now we need the antiderivative of f prime. So we would again go term by term in this example, and again reverse the general power rule in each case. So just on the first term, that means now we're going to add 1 to the exponent again and divide by the new result. That's where we get an x to the 8th, and then we're dividing by 8. We still have the other 7 down there because the constant got factored out. We factor out the negative 4/5. We add 1 to this exponent and divide by the result, so we get negative 4/5 x to the 6th over 6, which is right here. And so on and so forth. And then when we get to the constant, remember that the antiderivative of a constant is linear. So the antiderivative of c would be cx. And now we would need another arbitrary constant, and so we can call it d, or we can call it c2, or something like that. And we can check this answer right here by differentiating. Okay, always check the answer by differentiating. And you're not going to differentiate once here. This is f of x. We need to check to see that the second derivative of this function we found would be x to the 6th minus 4x to the 4th plus x plus 1. Okay, before we move on to one with an initial condition, that's where right now we're given a derivative, we need to find the original function, and we can find out what the value of the constant is by a given initial value. Okay, before we do that, let's try a couple more examples over here. Okay, for antidifferentiation in general. Okay, find the general antiderivative if f of t is equal to 3t to the 4th minus t cubed plus 6t squared all over t to the 4th. Okay. Now I'll note here that what's implied here in is the domain. The implied domain here is that t is not equal to 0. This is implied. It doesn't have to be given. Okay, it could be given that t is only greater than 0, but it wasn't. So it's implied that t is not equal to 0. And that's important in that when we look at our antiderivative, it needs to have a matching domain to the function we started with. But we're dealing with a quotient here. Okay, we cannot reverse a quotient. Okay, the quotient differentiation. We cannot reverse the quotient differentiation. Okay, at least not yet. Nor would we want to if we could avoid it anyway, I might add. So let's use some algebra. What kind of algebra could we apply? We can write each of these terms over their common denominator is one thing we could do. 3t to the 4th over t to the 4th minus t cubed over t to the 4th plus 6t squared over t to the 4th. Let's use a little bit of algebra because we can. And then simplify each of these. So this is going to be just 3 for the first term. We have minus 1 over t, or t to the negative 1 is that next term. And then we have, what is this, 6 over t squared. So we have 3 terms here. We can find their antiderivatives. I'm going to go ahead and write these last 2 terms as power functions, so that we can use the reverse of the general power rule. So f of t equals 3 minus t to the negative 1 plus 6t to the negative 2. Okay, and now we are going to reverse the general power rule to find our antiderivative. So big F of t. First, the first term is constant, 3, and the antiderivative of that would be the linear function. The input variable is t here, not x. So the antiderivative of 3 for this function would be 3t. Notice if we were to check the answer, we're going to take the derivative with respect to t, not with respect to x, but with respect to t, because that was the given input variable. The antiderivative of t to the negative 1, remember the domain. The domain is that t is not equal to 0. And the antiderivative with the general power rule when the exponent is negative 1 is a natural log function. In order to maintain the domain, we must include the absolute value. All right, that is important. Okay, remember the absolute value in order to preserve the original domain, okay, of the original function f that we were given. Okay. That is that t is still allowed to be negative, okay, and input into this result. All right, reversing the general power rule for this term, 6t to the negative 2. Well, we can just add 1 to the exponent, right? So what we're going to do, we're going to add 1 to the exponent and then divide by our new exponent. And then finally, to make a family of functions, we should put adding an arbitrary constant c. And now let's simplify this a bit to clean it up. 3t minus the natural log of the absolute value of t. Negative 2 plus 1 is negative 1. So we can move that to the front here and make this a minus 6. And then that is a t to the negative 1 and then plus c. There's an answer. How can we check to see if our answer is correct? By differentiation. F prime of t is equal to derivative term by term. This is going to be 3 minus the derivative of natural log of the absolute value of t is 1 over t. And then the derivative of negative 6t to the negative 1, we get negative 6. Okay, and then, all right, how do we find the derivative now? Remember, we move the exponent to the front, and then we subtract 1 from the exponent. Okay. And then the derivative of a constant is just 0. So I'll put a plus 0 there. Okay, is this equal to what we started with? 3 minus 1 over t. This is going to be plus 6 over t squared. Common denominator is t squared. Okay, right. The common denominator is now t squared. So we can put t squared down here. This would be 3t squared. T squared over t squared. This would be a minus t. We multiply by t over t. And this one is just a plus 6. Is this equivalent to what we started with? Well, what we started with, we had, here we go, t to the 4th, t to the cubed, t squared, and t to the 4th on the bottom. If we multiply top and bottom now by t squared, okay, t squared over t squared, we get what? 3t to the 4th minus t cubed plus 6t squared all over t to the 4th. And that does match with what we started with. So we did find the antiderivative. Let's try another one. Okay. Find f. Okay, the general antiderivative when you are given the lowercase f function. All right. Well, f of x is equal to 2 to the x plus the sinh of x minus 1 over the cube root of x squared. Okay, we know an antiderivative of 2 to the x. We talked about that. We know an antiderivative of sinh x from the catalog of derivative functions. And I'm going to rewrite this one as a power function. This would be, let's see, negative x to the power of negative 2/3. And then we can use the general power rule on that last term. So big F of x is equal to 2 to the x divided by the natural log of 2 plus, right, which function has sinh as its derivative? That would be cosh. Okay? And reversing the general power rule for x to the negative 2/3, add 1 to the exponent, so x to the negative 2/3 plus 1, and then divide by the result, negative 2/3 plus 1. Negative 2/3 plus 1 is equal to 1/3. Okay, so we have what? Big F of x. 2 to the x over natural log of 2, and I forgot to add my arbitrary constant c. There it is. Okay, then we have plus cosh x. Okay, right. 1 minus 2/3 is 1/3, so we're dividing by 1/3 right now. dividing by a third is the same as multiplying by 3. So I'm going to write negative 3, and then this is x to the 1/3, and then finally plus c. Check by differentiating now. Okay, the derivative of 2 to the x, okay, f prime of x. The derivative of 2 to the x over ln of 2 is going to be 2 to the x times the ln of 2, and then divided by the ln of 2. And those are going to cancel each other out, leaving us with just 2 to the x. The derivative of cosh x is sinh x. And the derivative of negative 3x to the 1/3 is negative 3 times 1/3 times x to the negative 2/3. And the derivative of the constant is 0. 3 and 1/3, that would just give us a 1. So we would have the last term is minus x to the negative 2/3, which is the same as minus 1 over the cube root of x squared. Okay, so now back to the notes. Finding a particular solution, okay, a particular solution when f prime is equal to t plus 1 over root t, can we find a function f such that the derivative of f would be t plus 1 over root t, and such that f of 1 would equal 5? That f of 1 is equal to 5 is called is a given condition that we can see would have to be true. And that's going to help us to find the constant. So let's start by finding the antiderivative of our f prime. Like in a previous example, we can divide each of these term by term by their denominator, if they have a common denominator, and then we can write them as two power functions. That works conveniently for this example. Then we can take the antiderivative by reversing the general power rule. Remember the arbitrary constant c. Here is our family of functions that are antiderivatives of this f prime. This is a family of functions. Now to find the constant c, given that f of 1 equals 5. So if we plug in 1 for the value of t, the output of this should be 5. That doesn't mean that c is equal to 5. It means the entire output of this function would be 5. So 5 is equal to 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2 plus c. And now this equation you can solve for c. Okay, and I've done that here. So c is equal to 7/3. So the particular solution, right, for this particular exercise is that f of t, okay, would be 2/3 t to the 3/2 plus 2t to the 1/2 plus 7/3. So you can verify it's the actual solution by, notice the derivative of this would give us back the original derivative function t plus 1 over root t. And again, f of 1 is indeed equal to 5. So it satisfies that given condition. Okay, let's apply that knowledge now. Where might we be in an application problem whereby we are given derivatives, or at least a derivative, and we're asked to find an antiderivative? Okay, an application where that could occur would be rectilinear motion. Suppose that we're given, for example, a velocity function. And if we wanted to find a position function relative to that velocity, well, we know that velocity is the derivative of position. Therefore, position is the antiderivative of velocity. Okay. Similarly, acceleration is the derivative of velocity. If we are given an acceleration function, then the antiderivative of the acceleration would be a velocity function. Okay, if we're given both acceleration and information about velocity, such as an initial velocity, or the velocity at some time within the given interval, then we can find a particular velocity function, and we can use that particular velocity function to then antidifferentiate again to find a position function. Take this example. Suppose that the acceleration function given is 3 cosine t minus 2 sine t. Okay, already we can find the general antiderivative of this, and we would interpret that antiderivative as a velocity function. Let's take a look at that. The antiderivative of this function is 3 sine t plus 2 cosine t plus c. Recall that the derivative of sine is cosine, but the derivative of cosine is negative sine. So when we check the derivative of our velocity function, when we check the derivative right? That's where we can observe that that's where the negative is coming from, because the derivative of cosine is negative sine. And the plus c is the arbitrary constant. So this is a family of velocity functions right here, okay, that would be associated with this acceleration function. Now to find the particular velocity function, given that v of 0 is equal to 4, that's saying that the initial velocity was 4. Let's say 4 meters per second, or 4 feet per second. The initial velocity was 4. So now we can find out what the value of c is. That's the initial velocity. We could also call c v0, so v subscript 0, okay, because it is the initial velocity, or it's where the input is 0. So we can solve for it by using this given initial condition. V of 0 is equal to 4, right? T is equal to 0, and the output would be 4. We solve 3 sine 0 plus 2 cosine 0 plus c is equal to 4. Solve for c, we get c equals 2. Here is our particular velocity function then. Now we can go further and find the position function. We were given acceleration, and we knew the initial position and the initial velocity, and that's enough information to determine a particular position function. So the antiderivative of our velocity, right here, the antiderivative of the velocity is a position function. It's a position family of functions here, the general antiderivative. And we can solve for the new constant by the initial condition for the position here, s of 0 equals 0. Right? So we plug 0 in for t. Remember the cosine of 0 is equal to 1. Right? So we end up with d is equal to 3. So here is the particular position function for that given information. Okay, let's find some other particular functions. Okay, example. Find a particular function. Let's call our function just f of t. The particular function as opposed to general function here. Okay, given f prime of t is equal to 4 over 1 plus t squared, and the condition that f of 1 is equal to 0. First, let's find the general, okay, the general antiderivative function. Well, f prime of t can be rewritten as 4 times 1 over 1 plus t squared, like we had seen previously. Well, then the antiderivative of that, that's just f of t, right, where I remove the derivative, okay, f of t is 4 times the antiderivative of 1 over 1 plus t squared. And the antiderivative of 1 over 1 plus t squared is the arctangent of t. And to get a general antiderivative here, we need to add the arbitrary constant c. Now we can use the given condition in order to find the particular solution. Okay, so we are using now that f of 1 is equal to 0. Now that we have f of t. So 0 equals f of 1, right, which is equal to 4 times the arctangent of 1 plus c. Now what is the arctangent of 1? Right, the arctangent of 1 would be the angle such that the tangent of that angle is equal to 1, and that angle would have to be in either quadrant 1 or quadrant 4, but tangent is positive in quadrant 1. Which angle would that be? We'll use radians here for that. We should be using radians, okay, because these are interpreted as real numbers here, not with units. So the answer to that would be pi over 4. So 4 times pi over 4 plus c. 4 times pi over 4 plus c is equal to 0. So we cancel the 4's. So pi plus c is equal to 0. Therefore, negative pi is equal to c. So our particular solution then, so therefore, our f of t is equal to 4 times the arctangent of t minus pi. And of course we can check through differentiation and checking the given condition. F prime of t is 4 times 1 over 1 plus t squared plus 0. Okay, so that's correct. And f of 1 is equal to 4 times the arctangent of 1 minus pi. That's 4 times pi over 4 minus pi, and that does equal 0. So that checks as well. Let's try another one. Find f given f triple prime of x is equal to the cosine of x. We've got, let's see, how about so we have f of 0 is equal to 1, f prime of 0 is equal to 2, f double prime of 0 is equal to 3. Find the particular function f. Okay, first let's find out the general f double prime of x. The antiderivative of cosine would be the function whose derivative would be cosine, and that is sine. So we have sine of x. The general antiderivative would be the sine of x plus c. Okay, so now we're going to use this condition here. F double prime of 0 is equal to 3. So we have 3 is f double prime of 0. So we're plugging 0 in for x. We get the sine of 0 plus c. So from that, right, sine of 0 is just equal to 0. So we get 3 is equal to c. All right, so f double prime of x, the particular f double prime of x, is the sine of x plus 3. There's our particular second derivative. Now we want to find the first derivative, starting with the general first derivative. So I have f prime of x, the antiderivative of the sine of x, whose derivative would be sine of x? That would be negative cosine of x, because the derivative of cosine is negative sine. Negative cosine x, and then the derivative, or the antiderivative of 3 with respect to x would be 3x. And then we need an arbitrary constant, and I'm going to choose d. Okay, or I could have called this, I'll call this one up here c1. I'll call this one c2. How do we find c2? We were given this condition. F prime of 0 is equal to 2. So 2 is equal to f prime of 0. Plug in 0 for x, we get negative cosine of 0 plus 3 times 0 plus c2. And now we can solve for c2. The cosine of 0 is 1, so we have 2 equals negative 1, and then plus 0 plus c2. Add 1 to the other side, we get 3 is equal to c2. So therefore, our particular f prime of x function is negative cosine x plus 3x plus 3. And we should be able to check that the derivative of our f prime would be this f double prime right here, sine of x plus 3. So now let's find f of x, starting with the general function f of x, the general antiderivative then of our f prime. So what function would be the antiderivative of negative cosine x? Well, we can factor out the negative, and then the function whose derivative is cosine would be sine, so negative sine of x. Now, the antiderivative of 3x, general power rule. We factor out the constant 3, and then we add, okay, and then we add 1 to the exponent, and we divide by the new exponent. That's our general power rule, reversed, right? Okay, so the reverse power rule was used there. And really, we're using the reverse power rule again on the 3, the constant, right? When we say, well, what function would have a constant as its derivative? That would be a linear function. So this is plus 3x. And then we need, for our general antiderivative, we need another arbitrary constant, and that constant is going to be c3. Now notice that it is not it is not going to be true that the given condition tells us the value of the constant directly. All right? It's not in general going to be true. Notice that for the second derivative, the constant c1 was equal to the 3, but in the first derivative function where the constant, the first derivative function where the given condition gave us a 2, the actual value of the constant wasn't 2, because the cosine of 0 was actually equal to 1. The given value of the constant was actually 3 there. So 1 equals f of 0 is negative sine of 0 plus 3 halves 0 squared plus 3 times 0 plus c3. And what do we get? Sine of 0 is 0. This is 0. This is 0. And plus c3. And we get c3 is equal to 1. Just that word of warning that these are not always going to be the values of the constant, but instead they're giving us conditions to find the constant. So 1 is equal to c3 in this case. And therefore, we now have a particular f of x function. Okay, negative sine x plus 3 halves x squared plus 3x plus 1. Now we should be able to verify that all of the given conditions are satisfied for f, f prime, and f double prime. And if we were to take the third derivative of this function, we can verify that that third derivative is just cosine x. We can do all that verification because of all the practice, of course, that we've done with differentiation. So in this example here, I give you the velocity the velocity condition, which allows us to solve for the first constant from antidifferentiation, and then the position condition gave us the second constant. Well, in the next example, I give you, well, what if we weren't given a velocity? What if we knew 2 positions and an acceleration function? What could we do? Well, in that case, what we do is we'd have to go through the velocity function straight to a position function, whereby we can write the position function where both of the constants are then incorporated into our general antiderivative in this form. So now we have our position function, and it has both of the constants c and d. Then the 2 conditions can be used at this, simultaneously, essentially, to create a system of equations. So s of 0 is equal to 0, and s of 1 is equal to 20, set up right here, reducing to these equations right here, and notice that this is actually a system of equations, and it's a linear system because the variables, in this case, the variables of the system are c and d. Right? They're just to the power of 1. Solve the linear system. This one's an easy one to solve, given that the first equation just tells us that d is equal to 0, so then we can just solve the second equation for c. So here ends up being our particular function that we get. Now, an example from physics. Right? Show that given that the acceleration due to gravity is approximately 9.8 meters per second squared, or 32 feet per second squared, or indicated downwards with a negative, show that given that information all by itself, a position function for an object, which is moving under the force of gravity near Earth, would follow a function of this form. The position function is 1/2 the acceleration times time squared plus the initial velocity times the time plus the initial position. Okay, and of course this then establishes for us why whenever we are seeing these functions whereby an object is being thrown near the surface of the Earth or dropped near the surface of the Earth, right, and we're investigating maybe the height of the function as it travels, the leading coefficient, first off, usually ends up being negative, depending on whether we're talking about the distance it's traveled or the height of the object, right, depending on the direction we're talking about. Oftentimes it's negative as a leading coefficient, and it's oftentimes half of what the acceleration due to gravity is. Like, we're so used to seeing that these types of functions start with a negative 4.9 or a negative 16 as the leading coefficients. If you take a look back through this course and into your previous courses as well, such as algebra, for those types of position functions or height functions, you would see that those are the most common leading coefficients as negative 4.9, negative 32, and now we see why. It's due to antidifferentiation. So let's say we're given that the acceleration, let's put this in feet per second squared. Let's say that the acceleration is negative 32 feet per second squared. Okay. What would the position function look like in general? So find a general position function, for an object near Earth if we're given that the velocity at time 0 is v0, that is the initial velocity of the object. So it could be the velocity when we initially observed the object moving. It could be the velocity of the object as it was hurled. And let's say that the initial position, s of 0, is equal to s0. That's the initial position. Okay, as another example, if it was an initial height, we could say h of 0 is equal to h0, if it was a height function. So we want to find a general position function, and a general position function is going to be a function of time, s of t. Okay, just given this information here, right? So we have acceleration due to gravity is negative 32 feet per second squared. So the acceleration function, a of t, equals negative 32. That's given. The associated general velocity function then can be found by doing the antiderivative. Okay, the antiderivative. So we can say this is the antiderivative of acceleration. Negative 32t and then plus c. Well, what is c? We were given that v0 is equal to v of 0. So v0 is equal to v of 0. So we can plug 0 in for t. So we get negative 32 times 0 plus c. So we get v0 is equal to c. So our particular velocity function is negative 32t plus the constant v0. That's our velocity function. Position function, s of t. The position function can be found as the antiderivative of the velocity function. Okay, so that's an uppercase V right there. So we get negative 32 times t squared over 2. That's reversing the general power rule right there. Plus v0 times t, right, antiderivative of a constant, plus a new constant. Okay, let's call this constant d. Given the condition that s0 is the output s of 0, we can then plug 0 into this. What's negative 32 divided by 2? Negative 16. That's where our negative 16 comes from for these models. And then we get 0 squared, and then plus v0 times 0 plus d, right? So in other words, d is equal to s0. Therefore, the particular position function we should use would be negative 16 t squared plus v0 times t plus s0. And that's the function that is used in so many examples that you would have seen since algebra class, such as, someone throws a ball into the air and modeling the height of the ball. Maybe it was thrown with an initial velocity of, 15 feet per second from a height of 6 feet off the ground. And then they would give you a height function, okay, modeled this way. Or if it were measured using meters and seconds, well, then that leading coefficient would be negative 4.9 instead, which is half of the 9.8, negative 9.8 meters per second squared. Okay, here's an example. Okay, a stone dropped from a cliff. Let's see, hits the ground at 120 feet per second. Find the height of the cliff. it seems like we're not given enough information almost here. We're really not given a lot. This is enough information for us to figure out the height of the cliff, it actually turns out. We're under the assumption here that this cliff is on Earth, okay? So, under the assumption that we're on Earth, then the acceleration due to gravity, which is directed downwards, in units that involve feet and seconds, the acceleration due to gravity would be negative 32 feet per second squared. All right? Find the height of the cliff, right? We want to build a height function. All right? Let's call it that. Build a height function to investigate h of t. That's a position function. We're going to start with an acceleration. The acceleration is negative 32. A of t is equal to negative 32. And now we can find a velocity function from that. A general velocity function would be negative 32t plus v naught, where v naught is the initial velocity of the object. Do we know what the initial velocity was? We were told here, in this case, that the stone was dropped. What does that imply? If it is dropped, okay, that implies that the initial velocity was equal to 0. It was just released. It was not thrown. Okay? Okay, this was just dropped. So if the initial velocity is equal to 0, then our particular velocity function is v of t is equal to negative 32t. Okay, so we have, let's take a look at a diagram here. All right, so we have an object was dropped. Okay, it fell down and it hit the ground. Okay, it's undergoing the force of gravity, negative 32 feet per second squared. And when it hits the ground such that its velocity at the time that it hits the ground, okay, the velocity at the time it hits the ground, well, let's see. It hit the ground at 120 feet per second. But the velocity would be directed downward, okay, because the object is falling. That's because we're building a height function, right? So the height of this thing was decreasing. Since the height is decreasing, as opposed to a distance function, since the height is, if we're talking about this in terms of distance, what distance did the object travel, then we could make velocity and acceleration both positive, by the way. If we're talking about just what distance did the object travel. But if I'm building it as a height function, okay, then I'm considering that, well, the height is changing, right, becoming less and less, right? So the velocity would be negative. So the information of the 120 feet, okay, 120 feet per second, that information is interpreted then as a speed. Okay, as a speed. Recall that speed is the absolute value of velocity. And again, we could have set this up with a positive velocity of positive 120, and we would have used a positive 32 as well, if we were just talking about the distance the object traveled, and we could. We could set it up that way. All right, so we have v of t is equal to negative 120 feet per second. Okay, at what time t? Not at all times t. I mean, here's how the velocity is changing over the time interval from the initial time that it was dropped until it hit the ground. That's the domain for this function anyway. Okay, that is, okay, right, the domain, here you go, the domain for our function here is that t is not less than 0, because at t equals 0, that's when it was dropped, and t is no more than the moment that it hit the ground. Let's say, we'll call this tg for when it hits the ground, so the velocity at tg, all right, the velocity at tg is equal to negative 120 feet per second. Okay, this is what a stone. Okay, so when the stone hits the ground. Okay, and then of course after that time, the stone is no longer moving along this velocity function, right? It's bouncing or it's stationary, right? It only is moving with this velocity for this time interval here. Alright, so what time is that? Okay, find the value of the time when it hits the ground. Okay, we can find that value by saying, well, we know that it's going to equal negative 120, right? This is a given condition that we have. Negative 120 is equal to v of tg, which is equal to negative 32 tg, and we can solve this then. So negative 120 divided by negative 32 is equal to the time when it hit the ground. Okay, here we go. Tg is equal to what? 3.75 or 15 over 4. Okay, so that's the time that it hit the ground, and that's important information. We want to know what is the height of the cliff. How can we find the height of the cliff? Okay, we can find the height function and determine what was the initial height. Determine h naught. That would be the initial height. If you were building this as a position function, earlier I said if you kept 120 positive and made a positive as well, then you're looking at a position function. So you're determining its distances traveled. And if that's the case, then you would be wanting to find the distance that it traveled over this time interval. Okay. But I'm building this as a height function. Take a look at the drawing. The height of the cliff is associated with the initial height of the stone. Okay, so let's determine what that initial height is by creating a height function. Okay, so we take our general velocity function right here, v of t equals negative 32t, and then we'll come back to this result here, the time when it hit the ground. Okay, but going back to this, v of t is equal to negative 32t for any value of t within the time interval that it's falling. The associated position function, which we're calling height, okay, so s is equal to, so position function is a height function in this example, is negative 32 t squared over 2, okay, plus the arbitrary constant, but the arbitrary constant would be the initial height. Okay, so that's the constant I'm using. All right, and then we can, right, then we want to find out what is the value of h naught. How can we find the value of h naught? Well, because we know the value of the height when it hit the ground. What is the value of the height function when we plug in the time that it hit the ground? Well, if it's the time that it hit the ground, then at that time the height of the object was 0 feet. Why? Because it hit the ground. Right? The height at this point is 0 feet from the ground. Okay? So using that information, that 0 is equal to h of tg. Okay? So here's what we have. H of t, the h of t function is negative 16t squared plus h naught. This condition here, 0 is equal to h of the time that it hit the ground, okay, is negative 16 time that it hit the ground squared plus h naught, which we can plug in, right? Negative 16, we had 15 fourths, or 3.75 was the amount of time until it hit the ground, okay, plus h naught. Negative 16 times, we have 15 squared is 225, 4 squared is 16, that works out nicely, plus h naught, these cancel each other out. So we get 0 equals negative 225 plus h naught. So therefore h naught is equal to 225. The initial height was 225 feet. Therefore the cliff is 225 feet, okay, tall. Okay, the top of the cliff is 225 feet from the bottom of the cliff. All right, one more thing I'd like to do here, and that is to take a look at back at Newton's first law of motion, which we can now prove through using Newton's second law of motion. Okay, Newton's first law of motion, also known as the law of inertia, okay, credit it to Galileo, and Newton did credit Galileo for having stated the law of inertia prior to him. Given no force, a body at rest, by body we mean a mass, right? A body at rest remains at rest, and a body in motion with constant velocity remains at that velocity. So that's Newton's first law, the law of inertia. Now, using Newton's second law of motion is that the time rate of change of the momentum is proportional to the force that is acted upon the mass and in the same direction as that force. That is, the force is equal to the time rate of change of momentum. Okay, and mass times velocity is the momentum. Okay, now if we take the mass to be constant, if the mass is constant here, then we can factor out m, and we get the derivative with respect to t of the velocity. In other words, we get force is equal to mass dv dt. Well, that would be mass times acceleration. Okay? So Newton's second law is commonly referred to in shorthand as force is equal to mass times acceleration. Okay? Use Newton's second law to prove his first law, that given no external force, a body at rest remains at rest, and a body in motion with constant velocity remains at that velocity. Now, proof of Newton's first law of motion. Given no force, so that is given that F is equal to 0. Okay, that means that mass times acceleration is equal to 0. But mass has to be greater than 0. Then that means that the acceleration must be equal to 0. If the force is equal to 0, then it's the acceleration that is equal to 0. Okay? And since acceleration, okay, is the time rate of change of velocity, right, or the derivative of velocity, then by substitution, dv dt is equal to 0, right? The derivative of velocity is equal to 0, and therefore what is the velocity function? By antidifferentiation, we have that the velocity function v of t, the antiderivative of 0, must be an arbitrary constant c. Okay? And that really completes the proof right there. We're saying that the velocity must be constant if there is no force that is acting on a mass. Because if there's no force on the mass, then the acceleration must be 0. But if the acceleration is 0, then that means that the velocity must be constant by antidifferentiation. Okay, so in other words, if the initial velocity was equal to 0, that means at rest, okay, then that means that the velocity for all time is also equal to 0, i.e. it remains at rest, okay, until such time that a force is acted upon it. If the initial velocity, okay, is equal to some constant, then the velocity function is always equal to that constant. Okay? This is in motion, right, with a constant velocity. Then v of t is equal to c. That means it remains in motion. Okay, with that same constant velocity. So I recommend that you take a look over the type notes, including the examples that I've worked through here. Review the particular derivatives of different families of functions. Perhaps have a table such as this nearby for the derivatives of different types of functions so that you can readily access what the particular antiderivatives for many examples may be. In addition to that, you're going to want to have the rules, the reverse rules, such as the reverse of the general power rule, which has these two cases, remembering the absolute value, remembering the arbitrary constant c, and the reverse of the rule for the derivative of the exponential b to the x. Okay, you always checking your answers to your antiderivatives by taking the derivatives. Okay, and practicing exercises whereby you are given conditions as well, recognizing situations where algebra is helpful in order to make the calculus easier to do. Okay, check out the homework here on WebAssign. Okay, homework problems should look similar in a lot of ways to examples that I've already done in the notes and here in the lecture video. And let me know if you have any questions. Okay, take care.